Alright, so this is module 1. So when you go to the instructional modules on Blackboard, you will see end up looking like this, instructional modules, and module 1 will be available. So just open that up. And then on the top it has the instructions, okay, for this particular module, and then you're going to be about the same for each module here on out. Make sure you do all of this online work prior to lab. It's very important. Have your programs, for the most part, programmed, the bulk of it done prior to lab. There's only so much machine time, and I want to make sure that people aren't sitting at a machine programming their entire workpiece when the machine should be cutting chips. It is very important that pretty soon we look at the mill assignment folder, that you take all the handouts that are assigned, print them out, hole punch them, and put them into a 3-ring binder that you could bring to class. This will greatly increase your efficiency in the shop. That is required. All right. There's a link down here, Discriminator CNC Edit Software download. Make sure that you download that on your computer. It is available on Hudson Valley computers or via Citrix. So either way, you'll be using this, and this will help you program your work pieces when you're away from a machine or a simulator. Okay. So let's get right into this. Let's get into the mill assignments. And then you'll see on the top here we have support content handouts. And you'll see we have the mill operator handout, the mill programming handbook, right from HAAS, feed and speed handout, G98 versus G99 handout, and then the speeds and feed data from Whittia. So all of these are very important. They will help you out, greatly in the shop. Let's take a look at this mill operator handout. So I'll click this, and this is what pops up. And then this is just the basics of the milling machine, the different types of milling machines. Okay, then it gets into the layout of the machine, what the parts are, way covers, if it has a presetter, the spindle location, back of the machine for maintenance, what's what, back of the coolant tank for maintenance, inside the computer or the control board of the machine, what's what. All right, that helps for diagnosing if you have an issue and you need to talk to a service tech. Gets into things to check periodically, the chip trap manifold for your coolant, what the grease is, and the spindle lubrication. Okay, and there are alarms and diagnostics on the machine controller for this. Then we get into machine axis motion on a regular vertical machining center, and this is going to be pretty standard throughout our shop. We do have a horizontal machine, and we'll cover that as needed. Gets into one big thing here is on the newer HAAS is the spindle will not turn on with the doors open, period. There is no override, so just something to be aware of. Then it gets into the overview of the actual controller itself, what is going on. This is really important to have with you at all times. This will help you greatly as you get used to running the machine. So you can go through all these and see what's what, all right, what the different mode keys, display functions, things like that. Edit keys goes through each one, what they are, file options in the editor, things like that. And then it just continues on into graphics, into manual data input, MDI mode, handle jog situations, jog selection, etc. Goes through loading a program, different file menus, off the flash drive, copying it off the flash drive onto the controller, or writing the program from start on the controller, things like that. Gets into your positions page for your work offset, distance to go, machine operator, or all, shows them all. And we'll talk about these individually later on. All right. And then it gets into the offset pages, which are very critical. Okay, so you have tool offsets and work offsets, type of tool, actual diameter, what all these different parameters mean. And sometimes you need them, sometimes you don't. We will use them in this class as needed. As we continue here, probing types, when we get into probing, we'll work on that, so don't worry about that for now. These are all probing cycles. Again, we'll use this later on. There's also another additional handout I'll have for you for the actual Renishaw probing on these machines. Then we get into different current commands, how to orient the spindle, what's going on the current commands, all these different tabs, what they do, all your macro variables, active codes, tool management, tool table, which is very important on a side mount tool changer, the quick calculator, different milling speeds and feeds in the calculator, etc. All right. So different alarms. All right, what they mean, how to work with a diagnostic screen, which is also important. All right, system information, etc. All right, so that's about it for this. This is very important to have with you. Okay, and everything else in here we'll talk about as we go. Okay, so make sure you print that out. Very important. Now, let's go back. And the HAAS mill programming workbook, we'll talk about this in a minute. This is when we start getting into program in this lecture, actual programming of the machine. We'll open that up. We have a feed and speed handout, which is something you should have on you. This is really handy. It has all the standard inputs, and then how to break it down into feed rate, spindle speed, and feed rates for drills. Okay, so very handy handout. What's one page? G98 versus G99 handout. This is for drilling can cycles. We will talk about this on the workpiece we're working with. This is very handy handout. And then we get into your tech data for WIDIA, like I talked about earlier. This should have been handed out in your previous classes. If not, here they are. They're the same handout, just a PDF version. Print these out and make sure you put them into your required notebook. Very important. All right. So that's the overview of the handouts. You're going to need all of these. And then we're going to get ready to program the first part. So we'll have a quick lecture on a whiteboard here about some of the basics of the machine, and we'll go from there. So we'll take a quick break. I'll pause the video, and we'll come back at the whiteboard. Okay, so I am in the mill programming workbook. Just for references, I know you're looking at a whiteboard now, but we are pretty much going to be focused on just the introduction page, which happens to be page 1. And then we're going to talk about the coordinate system now and continue from there. So basically, whether it's mill or lathe, we're going to focus on the mill in this video. The lathe video will be separate. We are working with Cartesian coordinates, so just X and Y positions. So you could really look at the machine and just imagine that it's you have 3 axes of movement. So you can look at your machine table and just look at a grid like this. And then you have X and Y. Okay? If we were in 3D space, we'd be looking down at the table right now. Okay? So what we're doing is we are pretty much programming and plotting points on this Cartesian system. Okay? So if you want to go, if this is 1 and 1, and you want to go to X 1.0, Y 1.0, that's a point. All right? Now, there are 2 main ways to program, okay, when it comes to these numbers. And I'll get you a reference here. On page 6, we start getting into absolute versus incremental positioning. And before we even get into machine codes, we need to understand that there's 2 different ways to program. And I typically work with absolute, which means you have a common 0. All numbers come from 0. So absolute programming, okay, or G90, just for reference, okay, that means common 0. Very important. All right. So no matter what numbers we are plotting, right, they all come from 0. All right. Now, incremental means that essentially you restart each time. So I'm just going to clear screen here. And incremental programming means that if this is our Cartesian system, right here, that if this is the first point and this is the second, it comes from 0 on the first point, but the coordinates re-0 from where you are. So that is incremental programming, or G91. Okay. And this is new 0. Alright, so there are times when you want to use this, but for the most part, I think it's wise to stick in the absolute positioning. And again, this page reference, the start of this, is on page 6 in the HAAS workbook. Okay, and take a look on page 8. So I'll bring this over now, what I'm looking at. Alright, so right now, here is page 8 in the text, in the supplied HAAS workbook. And this goes through G90 positioning. G90 is the G code, we'll talk about that in a minute, to tell the machine that we are absolute positioning. So all of these points 1 through 8, right, all come from this common 0. So point 1, okay, is going to be X, 1, 2, 3, Y, 1, 2, 3. Okay? Point 2 is X, 1, 2, 3, Y minus 1, 2, 3, and so on. Alright, so I recommend you work through that. Now, you'll notice it changes for incremental because it's going from point 8 to point 9. So if we go from 8 to 9, it's X minus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, Y minus 1. Okay? So a little different. So I recommend you do this. Alright, make sure you go through that. Very important. So, that is the basics for what we need for machine movement. Now those are just plotting points. Okay, so for our first example in drilling, this is ideal. When you go to milling, it's the same thing, except for you're going to have codes that essentially say draw a line or an arc from point to point, etc. So this is the basics of what we need to know for CNC programming. Whether it's mill or lathe, we are looking at it from a mill standpoint for now. There'll be another video in the lathe section to support that. So right now, what I recommend you do is work through this example on page 8 in the HAAS programming workbook for the mill. And I'll pause here, and we'll continue with the next area to talk about, which is going to be the initial codes and program formatting. Alright, so let's talk about some of the basic codes that we would use in CNC programming. So there are two main types of codes. There are G codes, okay, and M codes. G codes have to do with cutting. So G codes are going to be movements, things like that. Basically, these are what are called preparatory commands. Okay? M codes are things like turn the spindle on clockwise, end the program, rewind the program, turn the coolant on, machine commands. Okay? These are miscellaneous commands. Okay. So the page reference here in the HAAS workbook is page 11. Now they get into other variables here like character, word, block, positive side, trailing zeros. Just read that. That's not really a big deal here. We'll get that as we go. I'll explain them as we program our first example. Okay. One big thing here that we need to talk about is going to be, and just in case if I forgot here, the page formatting is page 10. And then it gets right into the list of often used preparatory G codes, which is going to be page 13 and on. So you're going to want to make sure that is somehow labeled in your notes, because you'll be referencing those quite often. But when it comes to these codes, one thing I want to mention, I'll clear this screen now, is some of these codes, okay, are what's called modal. And that means they remain on until you change it. Okay? That means that if you are working around a workpiece, let's say, we'll talk about our first initial code, this would be G00, which is a rapid command, that this is on as we go around a workpiece. If we're just trying to wrap it around a square, let's say we're just moving in this movement, you don't need to put G00 every single line. You just need it for the first one and it'll remain on the whole time. That's what modal means. Alright? So let's take a look at, just so I can show you here, the M codes. We get into M codes start on page 19 in the handout, and it goes through all the different ones you have, and these all apply to the HAAS machine specifically. Some machines have different codes depending on what brand they are. So some machines may use a standard M codes, some machines may have T codes, etc. It depends on what what brand machine you're working with. Okay. So that's the basics, and where we're going to leave off next is on page 22, and that's going to be program structure. And we'll talk a little bit about the program structure. Then we're going to skip ahead a little bit, and we're going to start programming our first component, which is the mill part 1 on Blackboard. And this is going to be one of the parts you're going to make. So I'll pause here, and we'll continue in a moment. Alright, so some of the basics about program structure. Again, I am starting on page 22 in the HAAS workbook. And make sure you read the first paragraph, goes through some what block delete, some of the backslashes, what they're for, things like that. But next page, if we get on page 23, we have some of the first things we need to worry about when it comes to our program. And the first thing we need to have is a % sign on the top of our program. There also needs to be one at the bottom, wherever that is. And that is very important. It tells the machine that, this is a CNC program, this is where it is from top to bottom. So it must be there. The next thing you're going to have is an O number. And I know that sounds like O number. It's going to be the letter O, and then up to a 5-digit program number. 1, 2, 3, 4, 5. This is where it goes on the list on controller. Okay. That number, you don't have to save it as that number. You can save any program as wherever you want. Usually there's 2 different file formats for this. It's going to be .txt and .nc. So when you save a program, and again I'll cover this when we actually program our first example, you could save, I save all my programs for the most part, if I'm doing onesie-twosie type work, as B dot whatever, because it's easier to type in. Now, on the newer machines, you don't actually necessarily have to type it in. You just select it, so it's sort of relevant. One of the big mistakes is that some people try to save their program as this number on the flash drive, and it doesn't work. That you don't need to do that. Generally, a lot of these O numbers, unless I'm doing sub-programs or there's some reason why they need to be something, I will just end up doing, let me erase this quick. Bear with me. I'll just do O, the year. Okay, whatever that is. Make sure this is, I'll erase this too. Get through to this. Make sure that you realize that this is the letter O. Okay? Very important. Now, usually after that, you're going to have something in parentheses, and parentheses end up meaning that it is just a comment. There is no, the machine doesn't necessarily read it, it's just for your reference. So in parentheses, we can put whatever we want. There is a numerical limit, okay? So just beware of that. It can't be a paragraph, but this could be example. Okay? Then after that, we get into tool information, work offset information, things like that. Typically, you're going to have, call up your first tool, so T1M06, all right? So load tool 1 into the spindle, all right? And then you're going to get into your initial commands, and that's going to have things like absolute. So it's going to be like G90. It's going to have things like maybe G20 for inch programming. It's going to have work offset information, so G54. And we'll talk about work offsets in a minute. It's going to have a rapid command to position it based on a work offset, and then turn your spindle on. All right. Then after that, you're going to have something that's going to go with a height offset, or something that controls the height in Z. Because G54, for what we're doing right now, takes care of X and Y. We still need a G43 comp. This is a height offset. We'll talk about that in a minute. Okay. You need to have a H value. All right. and then a movement. So to a Z 1.0. I know the text has 0.1. It's up to you. Okay. Let's talk about these two lines. We know about G90 or absolute positioning. We got that done. What we need to talk about now is G54 and G43, because that is where the machine and program meet. So your machine setup and program meet here with these lines. So what I'm going to do is I'm going to clear this right now. And let's talk about G54 through 55, 56, whatever it is. I'll give you a page reference. All right, let's take a look here. It's like page 45 in the text. Talks about G54 and the other work offsets. There's a lot of them in there. So basically what a work offset is it's a distance from the machine 0 to where your program coordinate system begins. So most machine tools, if not all, have a home position. So that is on the HAAS, it's the upper right corner. So that's up here. Okay, let's say this is the machine work envelope. It's going to be right there. Okay? That is the machine home. Okay, X, Y, and Z. Now, your part is going to be on the table, let's say somewhere here. And let's say the part 0 is right here. So this is part X, Y, and Z. Okay? The Z is going to be taken care of with G43, so ignore the Z for now. But in X and Y, we need some sort of distance from home, which is standard, to this position where our program 0 is, which is an X and Y work offset. Okay? And in our case, for a lot of cases, it's going to be G54 through G59. If you need more than that, there are other options on the controller. And this is just an area in the controller. On the offset page, it'll be listed work offset. And that is a data, that's where you edge find. That is 00 for the program. It takes care of these offsets for you. Okay, you could all program from the top right corner, but then you got to take into account this X and Y value in all of your points, which is not good. You want this to be a new 0 that the machine reads and then program from there. That's a work offset. And in the lab, I'll go over how to set work offsets, what they look like on the controller, things like that. That's the concept of them. Now, let's talk about different work offsets. Just for a quick thing, let's say you have the same part but multiple spots on the machine. You could have G54, 55, 56, and run the same program here, here, and here without having to reprogram the workpiece, just by calling up different work offsets. It's very handy. All right, let's talk about tool length compensation, which takes care of the Z for this. For the most part, there are times to set the G54Z. But you still have to take into account the tool length because that changes per tool. But let's look at that right now. So I'll clear this, and let's take a look at this from the front view. So what we're talking about now is going to be G43. This is cutter comp in the Z. So we'll talk about cutter compensation later, but this takes care of tool length offset, or TLO. Okay? So it says comp Z positive, okay, to a value, H1. This value is in the controller, and I'll talk about what we're going to do to change that up, or how to derive that value. And it's almost always wise to give it with a movement, Z 1.0 or 2.0 something. So compensate Z positive using this value going to this location in Z. Remember, before this, you're going to have G54 or whatever work offset on already. So the Z value, depending on how you touch your tools off, is going to be in there. Okay? So the first way we're going to touch off tools is if this is our end mill. I'll clear the screen. If this is our end mill, let's say it's an end mill, it could be a drill, whatever. And this is our part. Okay, this distance, all right, is going to be our H number, because we're going to take the tool and move the Z down and touch the tool here using a piece of shim stock. And you'll do that for each tool, and that is option 1. Okay, for touching off tools. That's what we're going to do in the lab. The first thing. There are a couple other ways to do this. Okay, you could actually touch off the part. You can actually touch off the part using, not necessarily using the end mill for each tool. So let's say you want to set your tools. What I usually do is, if I have a lot of tools I'm always using all the time, I'll have a set block. Okay, and this is our part. And what I'll do is I'll take the end mill and touch off all the tools, end mill, whatever they are, all the tools to this. And this will be TLO, or the H number. Okay. Then I will set the G54Z using a taut tool, the G54Z, to the top of the part. And that will be a G54Z number from the top of the block to here. Okay, this is convenient because that way all your tools can be taut to a 1, 2, 3 block, something standard, and as your part changes in height, okay, you only have to teach it once. You don't have to touch off all your tools again. All right, so this is option 2. Now, these are the 2 main ways we're going to do this in the shop until we get into the probing system and the tool presetter. So that's where I'll leave you for now on as far as how to set up the tools. Again, you could set up all the tools to the part height, and that's a quick way to do it. We'll do that first. Then the second way is best if you're the only one operating the machine and you're doing different parts but have the same kind of group of tools, all your tools already loaded. That way you only have to touch off once. So you have multiple part heights. You don't have to touch off all the tools every single time, and it saves you a ton of time. Okay? So that's going over the work offsets, the tool length offsets, and how they sort of can work together in Z. X and Y is sort of irrelevant. X and Y is all from home. Whether you're using option 1 or option 2, one thing I'll have to tell you here, if you're going to use option 1, G54 or whatever work offset, Z must be 0. Okay? Before touching tools off, has to be 0. Okay, very important. All right? Option 2, the G54Z should be 0 prior to touching off tools, but then we'll have a value once all the tools are already taut. Okay? And when we get into the shop, basically we are going to start from scratch every time. Every offset will be zeroed except for the probe. The probe will always have a value. You don't have to touch that off. Other classes are using the probing systems. So we'll cover more of this in the shop, but that's sort of the theory behind what we're going to be doing. So I'm going to pause here, and we'll continue. All right, so back on the Module 1 page here, let's start getting into the actual programming, and I think that this will help immensely. I don't find it valuable to go through each G and M code and describe what they are. We will describe them as we need them, and I think that is a much smoother way to do this. I find that sitting there trying to memorize codes is not worthwhile. You have to learn it while trying to use it. So what you need to do is download, this is a link to the CNC Edit software. Click this link, download the software, or use it on a school computer. Either way, you need this software. Okay? We'll get into mill assignments like we were before, and we'll look at mill part 1. And I'm just going to look at it in Blackboard here. And this is the part programming. And to keep it simple, we're going to program it just like this. Okay? There is a toothed out flatness. We are going to ignore that this example. We're also going to ignore the 3/8. These parts should be 3/8. But I'm not going to worry about facing this part off. The only thing we're going to do is spot drill and drill all of these 1/4 inch holes. Okay, we're going to ignore this chamfer. This would be our first assignment. There are a couple examples in this. So leave this open. I'm going to minimize the screen, and I'm going to open up Discriminator, and this is Discriminator I already have open. And I'm just going to go to File, New, and I'm going to go, actually I'm just going to save this. And I'm just going to save it on my desktop for this example. I'm going to call it example. Okay, mill 1. I'm going to hit save. This is saving it as a text. And what I'm saving it as is going to be what it's going to be saved as when I go to the machine. It's not a big deal, like I said, on the next gens because, or the new HAAS controllers, because you just select it. You don't have to type it in all the time. So it's okay to be somewhat longer. If this was an older machine or an older HAAS or a Fidal or something like that, I would actually just put B and .txt. Or you can save it as when you go to the machine. It's up to you. So I'm going to hit save. And now we're going to start with a percent sign, like we mentioned before. And then we could do an O number. So letter O, 2021. Comment line, parentheses, and this is going to be, let's just say example or mil 1. All right. And now we get into actually writing the code. Okay, and this is where the whiteboard talk really comes into play here. So what we need to do is let's give it some initial commands. Okay, so sometimes you can go T1 M6. We could do that. That's fine. I am going to ignore this. We're going to use tool 1 and tool 2 for this example. If you use the workbook or even the CAM instructor product, they have strict or predetermined tool lists. You could do that too. But for our setup on this first examples, or these first 2 examples, we'll just keep it simple, tool 1 and tool 2, because I want you to practice also clearing offsets when you're done. So let's we can call tool 1. So T1 M6, and what I find is that over here in parentheses, it's not a bad idea to put load tool 1, and this puts it in English, which is helpful. Now let's get into our initial commands. So we are going to need a G90 to go absolute programming. We could use G54 for our work offset. Right? And you don't have to put a ton on one line of code. You can break it up, so you can go G00 here. And I like to do that because it's easier to edit at the controller. So this is going to be absolute, work offset, rapid. So we have G90, which is absolute position programming, G54, which is one of our work offset options. This corresponds with a distance from home in the machine tool in the work offset page, and then a rapid G00. So these are all modal, but in particular G00, the next line of code, which is going to be an XY number, is modal. So it's going to rapid to that position. So if we go down here, and let's take a look at our workpiece here. If we go to mil part 1, I want to go to the first position. I want to be over this hole. So I'm going to go to, and we'll program it just like this. Normally you would want this workpiece, against a solid jaw. We are going to assume that these are already milled, that the block is already done for this programming, because that's what we're going to do in lab. We will hand jog the machine to create the 3-inch values on this, so that'll get some practice with hand jogging. So the squares are going to be established prior to this. So we'll put it right in the machine like this. We'll edge find this corner. This will be our work offset for this part, because we're only making 1. And then we can continue from there. So our first hole location is x.5, y.5. All right, so let's get back in the discriminator, and we're going to go to x.5, y.5. And tool 1 is a spot drill. All right. So now we are above the workpiece, the Z is at home, and we are at x.5, y.5. All right. So what we can do is a good idea, and this would be hole 1 location. Now, let's take care of our Z. So let's go G43, H1, Z 2.0. And I picked H1 because we're using T1, and it is good to keep those in sync. You don't have to, but it's good when learning. We are comping in Z positive, using value H1, moving from home to Z 2.0. Let's go over here and comp Z H1 to Z 2.0. So right now we are above the first hole. All right, tool 1 is in the spindle. All right. And the G43, we took care of our Z. Now, depending on how quickly your spindle will turn on, you may want to turn the spindle on here or after it. It's up to you. What we'll do here is we'll turn our spindle on, so we will go M3, which is clockwise spindle, and let's take care of the RPMs for this. Let's say this is a 1/4 inch spot drill, and let's look into, I just want to show you this here. Let's get back out of here, go to our support content, and let's take a look at our speed and feed handout. And you'll see we have spindle speed. So we have the VC, which is cutting speed, times 3.82 divided by the diameter of the tool. So if we break out our calculator, okay, the cutting speed we're going to use, this aluminum part, is going to be 200. That's going to be times 3.82 divided by, let's just say it's a 1/4 inch spot drill, 0.25 equals 3,056 RPM. So let's minimize this and we'll go M3S 3000, which is close enough for what we're doing. And we'll come over here with our notes. Clockwise spindle, 3000 RPM. Okay. So now the spindle's on. All right, one other option we could have in here is turn the coolant on. M8, coolant on. Okay. All right. So let's take a look at the rest of this. Now, we need to start drilling. So we talked about, and I'll look at the handout in a second, G99 versus G98 and how it affects the drilling commands or the can cycles. Okay, and we'll talk about can cycles. Let's take a look at the handout. In the handout, if we go back here and go to G98 versus G99, take a look at the code here, you'll see that we have a Z2.0 right before a can cycle. GD1 is just a straight drill can cycle. We'll talk about that in a minute. And you'll notice that we have G98, G99, and how it goes through. G98, okay, goes to the Z2.0 right here. G99, okay, goes to the 0.1, the retract value right there. So you'll see that we have a G98 going to Z2.0, and then we have a G99 going to 0.1, and you can use this throughout the can cycle to hop around things. So G98 goes to your previous plane, your retract plane, or not your retract plane, but your clearance plane, and G99 G99 goes to your retract in can cycle plane. Okay. So take a look. G98 retract 2.0, G99 or G98, not retract. Terminology here. I'll use Mastercam terminology. G98 is going to be clearance plane. G99 is going to be retract plane. Okay. So knowing that, we're just going to use the retract for this part. But the reason I brought this up is because this Z2.0, I always like to go ahead and go Z2.0 again, just because it's easier to change later. And this is going to be clearance plane. Okay? So if we do want to go to a G99, or if we want to change G98 to G99, we want to go to G98, we can change the value of that G98 very easily. Okay? So just something to keep in mind. All right? So now let's talk can cycles. And we are already at X.5, Y.5. And that is important because when you use the can cycle, we're going to use GD1 in this case, okay? It's going to drill the hole where you currently are first. Okay? So that means that when we go to G81, all right, R.1 retract value, that's between each hole. We're going to go Z minus, let's just say 0.450, or no, this is a spot drill. So we'll go down, let's say 60 thou. Okay? And the key here is that there's no reason to go to the clearance plane. So we're going to end up using G99. Now, some people say you should put the G99 here. It's up to you. Okay? So now this is going to spot drill, in our case. Now there's a GD2 spot drill cycle, but this is fine for us, GD1. This is just going to go drill. No pecking, no nothing. But it's going to drill this location first. Okay? Every position after this would be second hole, third hole, fourth hole, whatever. Okay? So let's pause there. I'll let you catch up, and we'll continue in a minute. Alright, so let's continue. Let's get our feed rate ready for this drill. We're going to use a 3 thou inch per rev spec for this drill, because drills are usually called out inches per revolution. Now, we could change our codes and interpret this in IPR, but that's kind of abnormal. So we have to convert our 3 thou IPR feed rate into inches per minute, which is standard on the milling machine. So I want to just go back into the speeds and feeds area on your handouts, and you'll see feed for drills, where your inches per minute equals your feed per revolution times your RPM that you're currently running. Okay, so let's take a look here. We have, okay, a feed per rev of 3 thousandths, so it's going to be 3 thou. All right, times N, which for us is 3,000 RPM. Okay, which is 9 inches per minute. All right, so let's get back into here and go F 9.0. All right, so now we have drill cycle. Okay, and let's just say I don't know, feed 9 I inches per minute IPM. Okay, and I think that'll work. I don't think it's worth putting anything else in there. Just drill cycle's fine. Now, can cycles. Why do we use can cycles? Because this can cycle is going to repeat this operation, the clearance plane value, the retract value, going down Z minus 0.060 at a feed rate of 9 inches per minute at every hole location, including this first one. So let's go to this next line of code, and let's take a look at our drawing. So I'll go back here, get out of our speeds and feeds, and we'll take a look at our actual part, which is right here. Let's take a look at our next hole location. So let's just work to the right. So we do not need to change the Y value. It's going to be a change only in the X value. So X 1.25, back in discriminator. So we'll go to X 1.25. We do not need to change the Y value. All right. So now it's going to spot drill at this location. Go to the next one. Okay. X 1.750. Okay. And we'll go to the last one for this row of X 2.5. All right. So now we have all of the X, X.5, X 1.25, X 1.75, X 2.5, 4 hole locations done. Okay. So let's take care of this for the next holes. Okay, notice that they're laid out square. So what we'll do is we'll get back into here, and what I'm going to do is I'm going to go to Y, and let's just reconfirm this. I'm going to change the Y value to Y 1.25. 1.25. And you could leave it here and go up to this hole, which is fine. But I'm going to go back to this one. Okay, so we'll go to X.5. So now I'm going to go to X.5, Y 1.25. So that's going back to this hole. Now I can copy and paste the X lines here. And it takes care of that because now we have a Y command. So let's go back down to this line, and let's go to X 1 point, or Y, I'm sorry, or X.5. Y, it should be 1.75 right here. Okay, then we can paste again. And you'll see what I'm doing here. I'll do the last one here, X.5. Y should be 2.5, and I will paste this again. So that should be all of our holes. All right, I am going to save now. Good to save often. And let's take a look at why we're using this software instead of Notepad, which we could do. So up on the top here, see the icon, you'll see Plot with Full Reviewer. I recommend you use this one. So right underneath Code Tips, Plot with Full Viewer right here. Click that. and then make the viewer larger. You have 4 windows by default. What I like to do is go right underneath desktop here, screens, go to 1. And in this viewer, if you hold down the middle mouse button, it's like a CAD system, you can rotate it around. You can right click and go fit. You could right click and let's go to views as isometric. And you can take a look. And we are going below. If we go to right click, view front, you'll see we are going down about a 1/16. Right? And this is the reason we use this software, because it helps us graph it. Okay? A couple things to look at is when we click in the program, it shows you what line of code is what. If you click on the graphics, okay, if you click on the graphics, it lines up with the code over here with that green box. So it's very helpful for editing. Okay, now by default, make sure this window up here you go to mill. Okay, if you have any issues, just hit the reset. That's what I did. You can backplot this through with this slide bar. I never found that super helpful, but it's there. And there's a player button, so you can watch this run in real time. Not real time, but you can watch it simulate. I haven't found that super helpful either. So that's this can cycle, right? And go ahead and plot those points, and we'll pause here and let you catch up, and we'll continue in a minute. Alright, so now that we have all these holes drilled, again, we'll just look at the plotter again quickly, and we'll see that we have the holes. It's all spot drilled. Okay, so now what we need to do is we need to send the machine, get ready for a tool change. So one of the things we could do here, after this, we have to cancel the can cycle. So all these positions are going to be drilled. All these positions are being read with this drilling can cycle. To turn that off, we need a G80. Okay, so G80 is can cycle cancel. So now this is off. So anything beyond that, the can cycle is not going to be working with. After that, we can, you have a couple options. You can bring the Z up. All right, so G00, Z 2.0. You can then go to an M9 to turn the coolant off, an M5 to turn the spindle off, and then we could send the machine. You could just do a tool change here, but one of the things I want to show you is the commands to put the machine in a position you want based on home position. So if we go to our reference here, I am in the workbook. We're talking about pages 49 and 50 in the HAAS mill workbook. You'll see the G28 method, which requires a G91, and then the G53 method. I do prefer the G53 method. The reason for this is to avoid any G91s in the program, because a G91 will remain on until you put a G90, and you can run into a lot of issues this way. So if we do the G53 method, G53 is the machine home. Okay, you're required to have a G49, which is cancel tool height. All right. And that will send the machine home. All right. The key here is, in our situation, we don't need the Y. We just want to send the Z home. We could just do a tool change. But I wanted to bring this up now because at the end of the program, this is very helpful. The G53 helps putting the table in front of you, things like that. We'll use the G53. So we'll get back into here, and we will go G53. G49 to cancel the G43 tool length cancel. So we go back to our workbook. Make sure you pay attention. Where is it in here? Right there. Just cancel your tool length offset with a G49 command when you do G53. Okay? Very important. So we'll get back into here. G49, Z 0 point. Okay? Just like that. Now, we could put the rapid in. We are rapiding anyway because this is on, so it's up to you. It's just redundant. It's not going to hurt. And now the machine is Z0, and the XY position is where we left off, and that's fine. So I'm going to save here, and let's go ahead and drill this workpiece. So now what we need to do is we need to get into here, and we'll put in comments here, drilling, and let's load our next tool. The other one thing before we do that, let's put an M1 here, just to start talking about this. M1 is op stop, And on the controller, you will see an op-stop button. And what that means is that when it hits an M1 and op-stop is on, the program will stop and wait for you to hit cycle start. Not a bad code. A lot of CAM systems kick that out, just to cover it now in process. So now we're drilling, and let's get into some changes here. Now, a lot of this can be repeated with a different tool. So what I'm going to do is I'm going to copy all of this right there, copy, and paste it down here. Because all we're doing is drilling these holes. Now right now it's still using tool 1. So we can get rid of tool 1 and tool 2. And load this, and this is going to be a 1/4 inch drill. Okay, this is good, this is good. The speeds and feeds are going to be fine because the tool is the same diameter. Okay, another key thing you got to watch out for is this H1. Make sure you go to H2, very important. Alright, get back in here. Next thing we need to change is the Z depth. So we could calculate how deep to go. The part's 3/8. If we go just 0.4375, that's fine for this example. I'm not worried about calculating the actual depth. I'm more concerned about the programming. So that should be fine. That should clear it, and we can continue on. All the hole locations are the same. The G80 is fine. This is fine. Everything's good here. And really, we could end the program here. Everything looks good. We could use a Y0 here to bring the table towards us at the end of the program to change the part, but that depends on the size of the machine. What we'll do is we'll change this M1 to an M30, which is program rewind, which means brings the cursor back up here to run the next part automatically. M2 will not. M2 is program end. It'll just leave the cursor here. So I like to use an M30. Then we'll just put our % sign. All right, so this program is done. I am going to save now before we plot it, and then I'm getting to the plotter. And you'll see now we have 2 tool colors. Green is tool 2. You can see if you zoom in, the red dot here is where the spot drill is, and then the green is where the drilling is. Now, that is drilling straight through. We're using the same can cycle. That could work on this thin workpiece. But let's say we want a peck drill. Okay, let's get back over in our HAAS manual, and let's look for our peck drilling, which is going to be G83. So let's look for it in our list here. So we got our can cycles. So starting on page 72, we have can cycles for drilling, tapping, and boring. And then make sure you read this, okay, now that you see a little bit of what we're doing with can cycles. All right, so take a look there. Gets into the G98 and G99, which is fine. We have a separate handout on that. All right, and we're going to use G83. Okay, intermittent feed-in, peck drilling cycle. So let's look for that cycle in the list. G81 is what we use. G82, I'm not going to worry about. That has a, you could put it dwell. I'm not worried about that. Just use G81. Here's G83. And with G83, we are going to end up using the Q value for this, which is a fixed peck distance. You can use the IJK method, which gives you an initial peck, the reducing factor of each peck after the first one, and the minimum peck depth. Okay, so to progressively step down in it. So if you have a deep hole, you can't have a heavier peck distance as you get deeper into the hole. You can progressively reduce how deep it drills each time using the IJK method. So you can read about that. Very, very helpful. We are going to use the Q value though. Okay, so it's either Q or IJK, not both. Okay, there's a quick example. Okay, so let's get the Q value. All right, go back to our software here. And we're in the drilling cycle here. We're going to go to G83. And the only thing we need to add is going to be a Q. Let's go 50 thou each. So that's going to be peck drilling now. Okay. So we'll get into here and just change this to peck. So now we're peck drilling. Okay. And that program is pretty much complete. So I'll hit save. And then what we'll do is we will take a break here. I'll load up a simulator so you can see the HAAS controller, and we can go over loading it onto the machine. All right, so we're back here in Discriminator. 2021 is our program name here, our program number, where it's going to go and list the controller. So let's go into File, Save As, and I'm going to save it as a text file, and I'm going to put it on the flash drive I have loaded on the computer. I'll save it as B. All right, not .txt, just B, because it'll be .txt here, and hit Save. Now it's on the flash drive. I will right-click and go to File Explorer and double-check that it is on my flash drive. There it is. And now I'm going to go over to the HAAS controller. So what you're looking at now is the HAAS controller. I'm taking the flash drive, and what I'm going to do is I'm going to hit what's list program on the controller, so you'll see that. And in list program, we have some options here. Up in the top here, right here, you're going to see USB pop up once I plug it in, and it initializes in the controller. There it is. So now I'll go up to the top, go over to USB, and I'm going to go down and go to B, which is right there. Now I want to load this, but I want to load it into the memory. So I'm not going to select program, because that'll run it directly off the flash drive, and you don't want to do that unless you have to. So I'm going to hit F2, copy. I'm going to go copy to memory, so let's hit enter, and hit enter again. And there is a 2021 file in there already. I'm just going to hit yes to overwrite it. So now the program's in there, it's in the memory. So if I hit list program again, it'll bring the orange cursor up to that top bar here. Cursor to the left, and you'll see our O2021 MIL1 file that we just loaded today. Okay, so let's go take a look at it. So I'm going to hit edit on the controller, and you'll see our program. I'm using the scroll wheel, the handle jog wheel, to work through right now. Okay, so let's take a look at this on the controller, or let's graph it on the controller. One thing you need to check is, now if you're at the machine tool, you have to have your tool set up and whatnot already. But on the simulator, I'm going to go into my offsets. I already have some offsets. They're sort of irrelevant on the simulator because it's not real. And I'll just check to make sure I have a work offset. And as long as you have values in there, you should be okay. Right? Because this is not dependent. This could be on a number of HAAS CNCs of different sizes. Okay, but you have to have values in there, especially when you're on a simulator. If you're at the machine, you should be, before you graph it, you should be ready to roll. Everything should be edge found or probed or whatever, and the tools should all be taught. So I'm going to go to Edit, Mem, Graphics. And here's our graphics screen in the HAAS. Okay, I'm going to hit cycle start and see if we have any errors. We look okay error-wise. I don't see any alarms pop up. And you'll see that up in the right corner is where our part is. It's not really to scale. So to fix that, we're going to hit F2, enable zoom, and I'm going to use the page down button in the middle of the controller and the cursor in the middle of the controller to zoom in, get this box zoomed in on what I want to see, which is right around there. I'm going to hit enter and hit cycle start again, and you will see our program run. Okay, so that's loaded in the controller. Okay, it looks pretty good. We got drill points. The work offset down here makes sense. Okay, I don't see any problems here. Some other things you can do is you can hit. One thing I want to show you here is I'm going to hit op stop, which is 3 buttons to the right of memory on the controller. So now op stop is on. I'm going to hit cycle start, and you'll see what happens. It stops at that M1 line. Before it didn't. So that's nice to stop if it's running good, but you want to stop it for the next tool. M1 is good. The only thing I will warn you is any M1 or MOO, the spindle will shut down. It may not kick back on again. It probably won't. So you got to make sure that if you do this mid-program, we are turning the spindle off anyway, turn it back on here. You need to make sure that it turns back on. Okay, so we hit cycle start again, and it'll run through. The other option is, if we turn our op stop off, turn single block on, which is 1 button to the right of memory, and it'll just single block through it. And you can see the Z cursor now do more. Down, up, as it goes. Okay? Looks good. All right. So a single block just works through 1 block at a time, which is very handy for diagnosing things. Okay. So that's about it for this example. Again, in lab, we will cover more of the controller, more of the details on the actual machine itself in person. But that is the programming and the basics for this first mill project. So if you have any questions, make sure you email me, and we'll see you in the next one.